Hey, feeling good, like I should. When in dark, walk around the neighborhood, feeling blessed.
Alrighty, welcome back. We're going to get into part 2 of our lesson about real numbers. We're going to start off, I guess maybe I'll back up for a second. We learned about patterns here yesterday about when you have a repeating decimal, it's not the same as just writing a terminating decimal as a fraction. When you got a repeating decimal, there's no way to identify the place where your last digit sits in, which gives your fraction its denominator. So how do we deal with that? Well, yesterday we worked through some of these problems and we noticed patterns. And those patterns are great. We're going to use these patterns to help us a little bit today, but there's also another process, and I'll give you an example of a problem where we would have to use this other process in order to figure out the fractional equivalent for a repeating decimal. So that's where we are here. And it says, Jessica wants to figure out why the pattern from problem 104 works. She noticed that she could eliminate the repeating digits by subtracting as she wrote at the right. See this, what we have right here is if you take 0.57 repeated, that's the same as 0.575757 all the way to infinity. So if you subtract a number from itself, you're going to get 0 for an answer, correct? So we are able to technically do subtraction problems that involve repeating decimals, even though we are not able to go all the way back to the far right digit and begin the process there. Because remember, 7 minus 7 is 5. I'm sorry, 7 minus 7 is 0, 5 minus 5 is 0, and so on and so forth. In this situation, we know if you go all the way back to the infinitely right digit, they're always going to match each other. So it's just as easy to say any number subtracted by itself is going to give you 0 for an answer, okay? So she thinks about this. She says, what if I multiply by something before I subtract so that I'm left with more than 0? And so there's a lot written in here. I don't like it. I find it confusing. I would prefer to teach it to you like this, but it's basically the same thing. It's just using information that I've already taught you in the past about how you can write equivalent equations by multiplying both sides of the equation times the same number. So what I'm going to do is instead of just saying 0.57 repeated is equal to something, I'm going to say x is equal to 0.57 repeated. And instead of writing it this way, I'm going to write it expanded out so you can see what's happening here. So if I decide that I'm going to multiply both sides of this equation times 10, then an equivalent equation would be 10 times x or 10x. But on the right side, because we're not able to multiply the digit on the far right because it goes to infinity, we have to just remember that anytime you multiply a number times 10, you either add a 0 to the right, like you would for like 6 times 10, or you move a decimal one place to the right, which is what's going to serve us here. So when I multiply 0.57 repeated times 10, it becomes 5.75 repeated, or 0.757575 all the way to infinity. If I were to multiply both sides of the equation times 100, then that would result in x being equal to 0.57577 becoming 100x is equal to 57.575757 to infinity. Okay, so does that make sense? The idea that you're multiplying both sides of the equation times the same thing, so it's a legal algebraic move, and we're purposely choosing to multiply times the power of 10, so we don't have to change any of these numbers. All we have to do is move our decimal points. So with that in mind, we're now going to use a little bit of algebraic strategery, if you will, to solve for x using two different equations, and it looks something like this. Let's just take this one away. If I were to take this equation here, the original, this equation here, come on, let's go. Come on, highlighter, you can do it. There you go. this equation here and this one here and do a subtraction, then 10x minus 1x would be 9x, correct? However, I can't do this subtraction problem because I don't have the same numbers in each one of the place values. So if we're going all the way back to infinity, where do you start? It's impossible to do. You cannot do that. So this is not going to work by simply multiplying this times 10. However, look what happens when I stop it. Stop it. There we go. Okay, look what happens when I multiply by 100. I take these two guys and we stack them up, and 100x minus x is 99x. And here we do get every one of those digits lining up. So 57.57 repeated minus 0.57 repeated. Oops, they're supposed to be repeated, are there? Let me just go ahead and fix that. There. They all the way going back to infinity, every single one of those will cancel out just like each one of these canceled out. So this minus itself is equal to 0. So on the decimal side, this is going to make 0. And on the whole number side, 57 minus 0, we can do that. So that becomes 57. So what we now have is this equation, 99x is equal to 57. Well, how do I solve for x? Let's divide each side by 99. And you get a giant 1 here, correct? So that cancels out, giving you x is equal to 57 over 99. Since we had already said that x was equal to 0.57 repeated, now we just think logically, if x is equal to 0.57 repeated and x is also equal to 57 over 99, that means that 0.57 repeated must be equivalent to 57 over 99. Now, this could be now simplified. As it turns out, oh, maybe you can't. That's 19 times 3. No, that's actually in simplest form. So we'll leave it like this. This is going to be the final fractional answer, which fits in with our pattern that we learned in problem 104. So let's use this technique rather than just using the pattern. Now, I'll tell you right now, based on problem 104, we've got 2 digits repeating, so it's going to be a 99 in the numerator, and then, I'm sorry, in the denominator, and the numerator is going to be 42. But I want to prove that this repeating decimal is equal to that, which, by the way, this can be simplified because I guarantee you both of those are divisible by 3, which means that, what is that going to be, 33, and that's going to be 14, so 14 over 33. Okay, but let's just focus on this right now. Let's not worry about the simplification of the fraction. Let's say that x is equal to 0.42 repeated. And if I multiply both sides times 10, that's going to make that 4.24 repeated. That's not going to help me. So if I multiply everything times 100, it becomes 42.42 repeated. So I'm going to choose to do the subtraction with these two equations. So what is 100 minus 1? That gives you your 99x. And what is 42.42 repeated minus 0.42 repeated? That gives you your 42. Divide each side by 99. And there you go. When you look at this one, you're going to have to multiply times 1,000 to get this guy over. So that's how you're going to end up with 312 over 999. Do you want to see that? Yeah, let's go ahead and work that one out. So we know that x is equal to 0.312 repeated. When you multiply that times 10, that only moves the decimal 1 place to the right. If you multiply it times 100, that moves your decimal 2 places to the right, which means it's going to be 312, then okay, yeah. And then when you multiply times 1,000, this is your first opportunity to have the repeating portion of your decimal match up perfectly with the original 0.312 repeated. So this is going to be 312.312 repeated. So if I take, come on, people, let's do it. If I take this one right here, there we go, and this one right here, then you're going to take the repeater part. It's going to cancel out and make 0. 1000x minus 1x is 999x. And 312 minus the 0 is 312. So when you divide each side by 999, you end up with this. Once again, this can be simplified, but I am not concerned about simplifying these fractions right now. This is hard enough to remember without having to deal with that. Okay, so let's just go ahead and finish this. We know the pattern. We saw it on problem 104. All two digits are being repeated, so it's going to be a 99. And the number in the numerator is 16, so it's become 16 over 99. Having trouble with my pens today. There we go. And then this 0.8 repeated is the same as 8/9. Now, I recommend you go through and check. Make sure those are correct. So let's take 14 divided by 33. Does that give me 42 repeating? Yes, it does. Let's take 312 and divide it by 999. Does that give me 312? Yes, it does. Let's take 16 and divide it by 99. 0.161616. Yes. And 8 divided by 9 is 0.8. Once again, they rounded that one off. It's 0.8 repeated. That's what we've got there. So you can double check it after you've declared your fraction answer. You can double check it with your calculator to prove that this fraction converts to that repeating decimal when you do the division. Okay, so that's how it works. I will tell you right now, this process is not very common. I don't know of too many situations in real life where you need to take a repeating decimal and convert it into a fraction, other than possibly when you're dealing with unit rates and you're going to use proportional reasoning and you want to set up a proportion instead of having a number in decimal form. That's pretty much the only way, the only time I can think of. I'm sure there are some others, but then there are so many other strategies that you can use for proportional reasoning that do you really have to change it to a fraction? I don't know, but mathematically it can be done. And for you math geeks out there, it's kind of cool to learn something new that works that you had no idea would work. All right, I want to show you this problem though. This is where you can't just use the pattern. The whole, I've got one digit repeating. How many 9s am I supposed to put in the denominator? What was the pattern? No, don't do that. This one requires us to say x is equal to 0.83 repeated. So if I took 10 of those, that is 10x is going to be equal to 8.3 repeated. And if I take 100 of them, that's going to be equal to 83.3 repeated. So which one of those two will work for me to do a subtraction? If I try and take 10x minus 1x, I get 9x, but then my decimals won't line up. If I try and take 100x minus 1x, I'll get 99x, but once again, my decimals don't line up. As it turns out, these are the two that you need to work with. So we're going to take 100x, which I know to be equal to 83.3 repeated, and then subtract away 10x's, and that's going to be 8.3 repeated. And what we get as a result is these guys cancel out, giving me my 0, but 83 minus 8 is 75. And 100 minus 10 is 90. So we end up in a situation where our answer is 75 over 90, which simplifies down to, what is that, 15 over 18? Which simplifies even further to 5 over 6. So is that repeating decimal equivalent to 5 over 6? I think it is. Let's take 5 divided by 6, and it is. Okay, So here's a situation where you didn't get a 9 or a 99 or a 999 in the denominator. You got something else. So that pattern that we saw in problem 104 does not work for every single repeating decimal. So this algebraic process, it's important to learn if you're going to learn how to convert any repeating decimal into its equivalent fraction. Great, problem 107. I'm going to give you a chance to do this work. Let me pull this guy up and I'll pause it. So take each one of these rational numbers, or are they all rational? No, there's some irrational numbers in there too. Take these real numbers and put them in order from least to greatest. And I can't think of a better way of doing it than putting them on a number line. Each one of these real numbers has a home on the number line. And once you find their home, then putting them in order from least to greatest is simply a matter of reading them from left to right on this number line. So I'm going to give you a chance to plug these in. My recommendation is to do this. Take and separate the negative numbers. Make sure they all go on the left-hand side of the 0. And then all the positive numbers, they'll be on the right-hand side. Do those first, and then put it all together to have them in order. All right, I'm going to pause the video and do it. You do it on your own, and when you feel like you've got everything in order, come back. All right, how'd you do? I looked at this and I said negative. All right, let me get rid of these guys right there. Start with the negatives, and negative 9 over 5 is pretty close to negative 2, but it's like negative 1 4/5 or negative 1.8, so that's right around here. Negative 0.75 is negative 3, so it's not quite to negative 1, so it's negative 3/4, so it's right around here. Pi is 3.14, and if you took 3.14 divided by 3, it would be a little bit more than 1. So one thing to be aware of is I'm not focusing on the perfect location of these numbers on the number line. I'm just estimating where they would go. And if there were two numbers that were so close to each other that it was hard to tell, then I would probably want to use my calculator to know for sure. But these are separated enough. 2/3 is, no, that is wrong. 2/3. You are here. 2/3 is less than 1. Where'd that be? Somewhere around there, maybe? Maybe right there. Okay, I'm glad I didn't write down my final order yet. So 2/3 goes here, which is less than 1. This is slightly more than 1. 2 1/4 is more than 2. And then the square root of 8 is an irrational number that's between 2 and 3, but it's closer to 3 because the square root of 8 is closer to the square root of 9 than it is to the square root of 4. So I'm putting it somewhere up in here. So now our final order is 9/5, negative 0.75, 2/3, pi over 3, 2 1/4, and finally the square root of 8. Okay. Now you do it yourself here. In this case, we don't have any negatives. So I'm not sure you really need to have a number line. Why don't you go ahead? I'm pausing the video. You pause the video, and you figure out the value of each one of those, or at least the approximate values, because some of them are irrational, and then put them in order from least to greatest. All right. So I don't know that these are exact, but I think they're pretty close. I just tried to round all of these to the nearest tenth, whereas that one went out to the thousandths place, so that's fine. So of all of these, the one I believe is the lowest value is 9 times pi, since 3.14 times 3 is going to be 9.3, maybe 9.4, maybe it should have been 9.4. But at any rate, I think that's going to be the lowest, so I'm going to write this as 3 times pi is going to be the lowest. And then the next lowest, oh, I am wrong again. That's okay, because I'm catching it. It's okay to make mistakes as long as you fix your mistakes before you turn something in, right? This one's the lowest, 9.099, then 9.3 or 9.4, whatever that's supposed to be. Then this is the only other one that's less than 10, so we're going to put that in next, the square root of 99. And then, what is it, 10 comes before the square root of 102, because this is about 10.1 or 10.2. And then 1.1 times 10 is going to be 11. That's going to be the greatest one. So what did we have? 1, 2, 3, 4, 5, 6. We got 1, 2, 3, 4, 5, 6, all in order from least to greatest. Alrighty, to wrap this up now, problem 109. Please read through each one of these problems, pause the video, and then once you believe, excuse me, you've got all the answers in correctly, then I will uncover each one of these boxes. And I'm going to give you the choices. Your choices are either a rational number, an irrational number, or a real number. Okay, so some of these can be used more than once. Decide which one you think it is. Okay, I'm going to assume you paused the video and then you've written down what you think are the correct answers. I'm going to reveal each one. The set of all numbers on the number line are called what? Every possible number that exists would be considered real numbers. So the set of all numbers would be all the real numbers that exist. The imaginary numbers, if you recall from a previous lesson where I referenced like the square root of -1 is an imaginary number, it doesn't exist in real life, that would not go on a number line because it doesn't exist. But everything that we've been working with, all the square root numbers, pi, all those numbers do have a home on the real number line. A number that has an equivalent terminating or repeating decimal, which one of these are either can be written as repeating or terminating decimals? That would be the rational numbers. And a number that has an equivalent decimal that is non-repeating, that means it goes on and on forever with no clear repeating pattern, those are the irrational numbers. And then any number that can be written as a fraction. Remember, rational numbers can be written both as fractions with integers in the numerator and denominator, or as their equivalent terminating or repeating decimals. So this concludes our lesson on the real number system. And the reason why we're learning about this is because when we do math like Pythagorean theorem, sometimes we get rational numbers, sometimes we have distances that we have to round off because to get to the distance we had to use a process that involved irrational numbers. So understanding that both of these numbers exist on the real number line, we tend to work with rational numbers more often than irrational numbers, and even when we work with irrational numbers, we have to round them off and make them rational. So we rationalize them so we can do computation with them. All right, so good luck on today's homework, and I will have there's a check for understanding for you to see how well you're understanding these basic concepts before we move on to an assessment that's going to be on Friday. All right, take care.
Hey, feeling good, like I should. When in dark, walk